Strong nucleophile? That's strong nucleophile? Okay, well, how would you confirm it, though, please? Confirm. Yeah, it looks like SN2. But how would you confirm that?
Based on the rate,
Rate? What would you look at?
if you do something to the concentration of the nucleophile, if you change anything.
Okay, if it was SN2, is a nucleophile involved in the rate determining step?
Yes.
Yes. So you could change the concentration of the nucleophile. If you change the concentration of the nucleophile and the rate changes, then that means it's involved in the rate determining step, and that means it must be SN2. But what if you change the what if you double the concentration of the nucleophile? First off, if it was SN2, what would we expect the rate to do if we double this? The rate would double. What if we double this and nothing happens to the rate?
It's not SN2.
Sounds like it's SN1. Because this is a secondary carbon, it is a little sterically hindered. I said SN2, but most likely, yes. Now there's no stereochemistry here. Well, actually it is, but it's not. It's apparently racemic here. We could also tell by if the reaction gave inversion or not versus racemic. If we had some stereochemistry to find here. Yes, we can do rate to confirm, right? There's another SN2 reaction down here. Once they remove the ester from this nitrogen, then they react it with this guy and it displaces the chlorine. That's how they make that bond there, and that's likely an SN2. Okay. I sent you the answer keys to the page I showed originally before that. Please ask questions if you have questions. That's a substitution. We'll have a quiz on Wednesday. This is now Monday. I don't know why we're not going to be here on Wednesday, but I reckon we haven't been here on Wednesday in a few years. Quiz on Monday. Test on next Friday.
Next Monday. No, next the following Monday, December 4th.
Yeah, you had it conflicting in your syllabus. It says December 4th, but in your calendar it says it's on the Monday.
It says Monday where? Well, in regards, Monday's the last day of class, so the mistake.
Wednesday is the last day of class, December 6th.
Oh, the last day of class was on a Monday. Okay, when? Okay, I'll have to look at this. I thought last day of class was on a Monday, that's why I had to be on a Friday. Okay, let me look at it. In any event, quiz on Monday, a week from today. If it is on the following Monday, that's good. It gives us another weekend. But all right, E1, E2, elimination. There's elimination showed here on the cover page. Compound 63 going to 64. Synthesis of Tamiflu, antiviral flu drug. If you look at 63, we have an iodine. That's an I. The iodine is being removed. It's being eliminated. When we eliminate, we put in, we're making alkenes. What's being eliminated from this compound is the H here and the I there. So ultimately, we're removing HI. We're eliminating HI when we go from here to here. So, that's an example. We will call that an E2. Okay, elimination. This is set up just like the beginning of the substitution. The general line reaction, you're going to have a carbon with a leaving group. Of course, tetrahedral carbon, right? Tetrahedral carbon with a leaving group. We're going to have a base. This is going to be analogous to our nucleophile. But here, this guy is going to take an H. And when it takes an H, we call it a base. Typically, they're a lone pair. And when we eliminate, we're making alkenes. The leaving group will leave. It takes on a lone pair. But the base takes the H. So this guy loses an H and the leaving group. And we are eliminating because nothing is added to this. We're not doing a substitution. We're not replacing anything. We're just eliminating. Now, it's also called a beta elimination. That refers to the hydrogen that's eliminated because the leaving group on the first carbon, that's called alpha. The next carbon is called beta. And we're losing an H from the beta carbon. So that's where the beta comes from. It's referring to the hydrogen that's removed. Okay? So we're doing leaving group chemistry, leaving group on tetrahedral carbon. An example down here. This alkyl bromide, we can react with this base. We can do a beta elimination, make alkene. Leaving group has left as bromide, and the base has taken the H. And so we have eliminated HBr from this molecule. A lot of times you can write, I did this before, once you eliminate, that's what we eliminate from this effectively. Now we didn't form HBr. Okay? But this is sort of the atoms that we're eliminating in the form of HBr. All right? What's the mechanism for this reaction? We'll do two possible mechanisms and then we'll look at them each and see which one looks best for this example. First, we're going to call it E1. E1, the first step is the same as SN1. Thus, what is the first step? Just leaving group leaving. Same as SN1. Because the leaving group does have to leave. So let's just have it leave. And that would form what? Carbocation plus Br minus. Now hopefully you already see that we don't like this mechanism because what type of carbocation did we form? Primary. Bad. But let's do it anyway because this is going to be the illustrating of our E1 mechanism. Okay, already made the bromide. We got to make the alkene. We got to make the base takes the H. Well, we got two H's here. This guy could add to the cation, and we could have the oxygen bonded here. So that would be a substitution product if the oxygen is then bonded there. And an alternative is for this guy to act as a base and to take and to bond to this H. And these electrons just sort of fall in here as the pi bond. Now what does that electron movement do?
Okay.
We have now made everything. Because right here, the base takes the H, and that's the alcohol on the end. If these electrons move in and make pi bond, what does that give? Well, that gives you your alkene. So there it is. That's an E1 mechanism. 2 steps. What are the 2 steps? LG leaves. Let's call that, yes, that's what it's doing. Another thing we can see is ionization. Leaving group leaving is ionization. What do you want to call the second step?
Beta elimination.
Acid base chemistry.
Yeah, it's strictly your beta elimination because here's where you're taking the beta hydrogen. The entire process is sometimes called beta elimination. More precisely, base takes beta hydrogen. I mean, that's the second step here of the E1. Which one's rate determining? Ionization, same as SN1. That means this is fast. Now if we graph this, we start out with our alkyl, let's call this A, got a carbocation B, and then product C. A, B is our carbocation, higher energy rate, and then C, where can we place C compared to A? C would be higher or lower in energy? Be higher, right? Because what are we doing here? We're breaking two sigma bonds and forming a pi bond, a weaker pi bond. It should be higher. Here we go. There's your rate determining step. And then removing the proton doesn't take much energy. We come down to our alkene, right? We're removing HBr. Elimination. Elimination is the exact opposite of what?
Addition.
Addition. What if you had this and you added HBr? Have we ever did that reaction? Have we ever had an alkene and added HBr?
Mm-hmm.
That's the first type of reaction we looked at. So it's the opposite of that. But it's leaving group chemistry. Back then we were doing alkene chemistry. So you can cycle here. You can go from one to the other. And remember when we went that way, it was exothermic. Coming this way, it's actually endothermic. Does that mean the reaction cannot be done? No, you can do endothermic reactions. You just apply some heat. And supplying heat, that doesn't mean you have to heat them because maybe room temperature is enough heat to get them to go. Questions about this? Why is it called E1? Well, of the two reactants, how many are involved in the rate determining step? Only the alkyl halide or alkyl tosylate or whatever your leaving group is. The base is not involved, so it's called an E1. But the model reaction, this is not the mechanism for the model reaction. It's bad. All right? There'll be other reasons why it's not the mechanism. For example, the base is strong. What do we say if our nucleophile / base was strong? Reaction will always be bimolecular. This is going to be a bully. It's not going to wait for this to ionize. This is an E2 mechanism. Let's look at E2. So E2, both substrates are involved in the rate determining step, right? we go. Let's do it again, but let's do E2. What's another way we can do this? Show a mechanism. What's another mechanism we can show?
The bromine leaves as the oxygen takes the beta hydrogen.
Do what?
The bromine would leave as the oxygen takes the beta hydrogen and the pi bond is formed.
Okay. Either you've done some reading or you
I'm just really smart.
have what? Well, the other way is do it all together now, concerted. All right? I'm just going to go ahead and do it. It takes the H. These electrons move in here, and these get kicked off. All concerted. Everything all at the same time. What would that arrow movement give? It gives all that. Hopefully by now you know what arrows are doing, right? This is making bond to H. Well, there it is on the end. What is this arrow doing? These electrons are falling in to make an additional bond. That's the alkene. And this is moving on to the bromine as a fourth lone pair. There's your bromide. All together now. Okay? This is concerted beta elimination. How many steps in this mechanism on the board? Just one step. Which one's the rate determining step? That step. Are both involved in the rate determining step? Yes, it's called an E2. Both are involved in the rate determining step. If we graph this one, what would it look like? This is A, and this is C. Is that right? We go from A to C. What do we have? There is no B. There is no intermediate. What do we have? You just got a transition state. You just got a, right? This is your transition state, right? Just one transition state. Over here, of course, we had two transition states, right? Transition state leading to the intermediate, and a transition state leading to the final product. What does a transition state look like? It's where all these bonds are partially forming, partially breaking. It's where this is partially forming to H, this is partially forming an alkene, and this is partially breaking. Be lots of partial bonds. When all that's happening is that was the transition state between here and here. Higher in energy when that's happening. Okay. We'll talk more about that. This mechanism is E2, mainly because we have a strong base. It's a bully. It's not going to wait for the leaving group to ionize. Just like the strong nucleophile is not going to wait for the leaving group to ionize. All right. Is there another way to do this mechanism? Is there another possible way? Another possible mechanism?
The hydrogen is taken first.
What if these electrons just take the H and we just leave those electrons there like an acid, a typical acid-base reaction? Boom, boom, boom. We make that plus, that now has the H. We didn't do this before, so this would be a third mechanism. Now what would we have to do to get the final products? What if these electrons then came in here and sort of kicked that off? Which do you propose would be the rate determining step here?
The first one.
What?
First step.
First step, making the high energy ion. Making the high energy ion. But over here, this was a carbocation. High energy ion here is the anion. Then we fall down here when we make the neutral alkene. Yeah? So this is a third possible mechanism. We did not do this in the previous two. We made an anion. This will never be the mechanism for this semester. Okay, we either do E1 or E2. Sometimes you guys want to do this. Here's a big thing. This H, which we removed before, is not acidic. That's just a hydrocarbon H. No acidity. We're never going to make anion here. This mechanism is sometimes done in organic 2 whenever you have a very acidic hydrogen. Okay? I'm not going to even tell you the name of this mechanism. But we're not doing it. We're not making anion. We go back to the previous page. In the E1, it takes the H, but it's taking the H from a positive species, right? Look at the E1. When it took the H, the thing it's taking the H from, that's a positive charged molecule, right? You're looking at your paper. Right? In E2, it takes it from a neutral molecule, just like it did in the third one. But in E2, did we form an anion? Did we form a carbanion? We did not form a carbanion. It takes it and you get the final product all in one step. Okay? We did not form a carbanion. The third one we did, but I'm telling you we're not doing that. That's not one of the mechanisms we're going to be doing. Okay, E1, E2. Our example reaction is E2, mainly because we would never form a primary carbocation. And also, we got a strong base. Let's look at C. Alternative example. Take this compound and heat it with this neutral alcohol or no solvent at all. You could just do this with no solvent. Neat. We can get the alkene plus HBr. We can eliminate HBr. Mechanism for this reaction. Do you think this reaction is E1 or E2?
E2. E1.
Bimolecular reactions require strong nucleophiles, strong bases. SN2 requires a strong nucleophile, right? Well, an E2 requires a strong base. This was on the summary. And I told you we haven't covered E2 yet, but it was there. It said, strong bullies are going to be bimolecular. And to do a bimolecular, you have to have strong bully. Do we have a strong base? Somebody said yeah?
No.
How do you what's a strong base? Anions or sp3 nitrogens, just like nucleophiles. We don't have either of those. No strong base. This is going to be an E1. First step of E1. Same as SN1. Leaving group leaving. that plus Br minus. All right, how do we get final products from here?
Br takes the pH.
Something taking the H. Okay. What can take the H? Actually, a leaving group can turn around and take the H, and that would give us HBr. Or you could use, if that was water, that's essentially like water, it's a neutral oxygen, that could possibly take the base. But this could work with no solvent at all. This could just take the base, take the H. And so these electrons take the H, these electrons move in. But hold on, let's look at something. Right here, these two groups are sort of cis. If we put the double bond in, they'll be cis, right? Let's don't do this here. Let's go back to September. How is this thing going to more favorably exist?
Trans.
If I had models like this, or would it prefer to exist anti? Syn or anti? I have free rotation here. This thing's going to rotate. And this is like syn and anti. This is just rotamers. And this is going to, these rotamers are going to be in equilibrium. Which is going to be favored?
Yeah.
It's just going to rotate. In fact, starting material could rotate appropriately. It's just drawn in a certain way there, but to get it drawn in this way, we can just rotate it. Now let's remove a hydrogen and electrons fall in, and what does that give? Transalkene plus HBr. The ionization would be your rate determining step, and we can call this fast. And this is sometimes glossed over. It would not be a rate determining step, so I reckon you would also call it fast. The problem is, if someone looked at this outside of what we just said, they might say, well, this is one intermediate. Yeah, it's one intermediate, but that one intermediate can rotate. So how would you do this on a reaction coordinate diagram? I wouldn't worry about this on a reaction coordinate diagram. That's a classical E1, weak base, definitely not a strong base. And to point it out that sometimes you can just take these guys and just heat them. And they will eliminate like HBr. It's a thermal elimination by such an E1 mechanism. And the leaving group turns around and acts as the base. Summary statement at this point. An E2 elimination requires a strong base. We've already said that, yeah? Thermodynamics and entropy for elimination reactions. We've already kind of said that. First reaction, when we looked at it, was actually endothermic, right? That's really nothing new. I mean, you could have figured that out right on your own. Entropy. Entropy. Well, let's just look at the reaction we just did. Forget about the solvent. We didn't even use it in our mechanism. Is that reaction favored by entropy? Yes or no?
Yes.
Yes. One molecule going to two. It's eliminating. It's breaking apart. Yeah, it's favored by entropy. But it's not favored by enthalpy because we're going from 2 sigma bonds to a weaker pi bond. Okay, in the previous examples, well, actually in this one we had something that we didn't point out. And in the next page, we're just going to start pointing it out. That is, why did the Br take this beta hydrogen? This is the alpha carbon. The alpha carbon is the carbon the leaving group was on. The beta one is the next door. But isn't that a beta carbon as well? Yes. And doesn't this beta carbon have hydrogens? Why didn't they take this H and these electrons move in? We could have put an alkene here.
Yes, the alkene.
Let's look at that on the next page. That is regioisomers. Look at the first beta elimination reaction. There's only one possible regioisomer. Because that's the alpha carbon, there's only one beta carbon. Thus, there's only one type of beta hydrogen. There's 2 there, but they're identical. So there's only one type of beta hydrogen, because there's only one beta carbon. Now, the idea that they're identical, we will sort of modify that, because in some examples they will not be identical. We'll have to look at their orientation to the leaving group. Okay? But in the end, because there's only one beta carbon, you're only going to get one possible alkene, eliminating from that beta carbon here. There's no other possible alkene, unless you get a carbocation rearrangement or something. All right. But look down here. If we do a beta elimination of this guy, it's actually 3 possible products, because you got 2 different beta carbons. Alpha beta or alpha beta. If we remove an H from this guy, we're going to put a double bond in between these 2 carbons. And that would be here. But this guy has a stereoisomer because it can be E or Z. Now one may be favored over the other. It depends on the mechanism. Now if we put the H, if we remove this H, we can put the double bond over here, and that would be this product. Well, this product does not have a stereoisomer. That alkene is not stereogenic. That's why up here there's only one possible product, because not stereogenic, there's no stereoisomer. So the reaction at the top is like, in terms of regio and stereo, there's only one possible product up there. This one has 3. These being regioisomers. Those 2 being stereoisomers. So which alkene will be formed in this slower reaction? Well, it depends on a variety of factors, including mechanism, whether you're doing E1 or E2. Depends on the base used. Depends on the orientation of the groups. That is, the H and the leaving group. So let's try to answer this with the next few things here, including the next page. Here's one statement. The most substituted alkene is called the thermodynamic product. Thermodynamic meaning most stable. The most substituted alkene is the most stable. We've talked about them numerous times. Okay? In the context of elimination reactions, the most substituted alkene is called the Zaitsev product. And nobody knows how to spell Zaitsev. Some people spell it with a Z, like Zaitsev. It's Russian. Okay. And I think actually Zaitsev worked with Markovnikov. Okay? Russian chemist back in the late 1800s. So the Zaitsev product. So look up here. Which one of these three is the Zaitsev product? Or is it more than one? Is that the Zaitsev product? No, that's the less substituted alkene. It's only got one substituent, one carbon substituent. These alkenes have two carbon substituents. So there's two of them. They're both more substituted. These are your Zaitsev products, okay? But the Zaitsev products have stereoisomers. Right? The Zaitsev is always, okay, let's underline that twice, the major product in the E1 elimination. So if you're doing an E1, if this occurred by an E1, those would be your major products. Then we'd have to think about stereochemistry. The Zaitsev is not necessarily the major product in the E2 elimination. E2 can often give the less substituted alkene. This would be the less substituted alkene. It's called the Hoffman product. Less substituted is called the Hoffman product in the context of elimination. So what did we just say here? E1 always gives which product? Zaitsev, which is the most substituted alkene. E2 gives which one? E2 gives which one? Okay. Give either one is major. Okay. E2, we're going to have to look at some unique things. E1, always Zaitsev. By the way, let's go back to the previous page. What mechanism was this here? C? E1 or E2?
E1.
E1, so we should have gotten which product?
Zaitsev.
Zaitsev, more substituted. So why did we put double bond there and not there? If we put double bond down here, it would have been this double bond here. Why didn't we put double bond there? That would have been Hoffman. We got Zaitsev. So we got it back over there, we just didn't call it that yet. Okay? That's why we did it. Now we can get into, that's a shallow explanation. We could explain further. And this is sort of a repeat right here. All right, let's do this reaction here. We take this with water, probably some heat. Heat and water, we get this alkene plus essentially HBr and water. But we know HBr and water is going to be H3O plus Br minus. Okay, so we can eliminate HBr. This is an E1, right, because there's no strong base. It's a weak base. Water's a weak base. Since it's E1, we know we're going to get the Zaitsev product. We got two different beta carbons. But are we going to put double bond here by removing that H Or we're going to put double bond here. Or we're going to put double bond here. We're going to remove that H.
In the middle.
Because we make the tri-substituted alkene. If we ever removed this H, it would have been a monosubstituted alkene. But we don't get this product in the E1. We get the thermodynamic product, the Zaitsev product. Now, does this product have any stereochemistry? Is this alkene stereogenic? No. There's no stereochemistry. It's not stereogenic. But if it was, would we get E or Z? Which is more stable, E or Z? E, right?
Mm-hmm.
Which is the same as trans. E is the largest group's opposite.
Mm-hmm.
That's going to be your most stable. Let's go back up here. So if this reaction was E1, which of the three would be your product?
E. E and Z.
That one, right? It's the most substituted. And the bigger groups are opposite. It's the most stable. The most stable is always the major product in the E1. Because again, you could have two Zaitsev products, one cis, one trans. Well, then you can determine of the Zaitsev which is most stable. Well, it's going to be essentially trans or E. That's a thermodynamic outcome. Most stable product. What about E2?
Depends on the product.
First thing we'll look at is base dependent. Depends on the base used. Look at these two examples. Here, we're using hydroxide. First off, we're doing E2, so we must have a strong base, right? E2 requires a strong base. Hydroxide is a strong base. It's an anion. So, hydroxide, we're going to get the Zaitsev product because we can. You always get the most stable product if you can. You get the most, still get the most substituted product. The thing we have to point out though is it's taking this hydrogen to make the double bond here. A concerted elimination all at the same time. The thing we have to point out that this hydrogen is actually quite hindered. It's sort of buried between the two methyl groups. To get the Zaitsev product, you have to remove the more hindered hydrogen. That's okay if the base is small. If the base is large, we have difficulty taking the more hindered hydrogen. And a larger base, such as butoxide, because it's got this substitution, it's got these wings here, it's a larger base, it's going to be more prone to taking the other beta hydrogen and give the Hoffman product. Because typically, to give the Hoffman product, that beta hydrogen is more accessible. And it turns out that's all the time that way. You see how this H is sort of right next to these two methyls? And it's sort of buried in here. If we put the H's on here, sort of buried in there. But this guy, there's just H's here. It's just more accessible. I mean, over here it's wide open. This can come in here and take it. Where here, it's like, I can't get in there. The more accessible H leads to the Hoffman product. That's the outcome you typically get when your base is sterically hindered. Okay? Sterically hindered. Hoffman product, less substituted. Now the Hoffman product is also known as the kinetic product. Because look at this. Compare these two. Which is more stable? It's more stable. That's your thermodynamic product. But down here, why was this one formed? Not because it's most stable, but because what?
The base is big.
It's faster. It's faster because this H is more accessible. And so we call this a kinetic product because it formed faster. Okay? Please look ahead. Size of the base is important. Next topic here will be orientation of the leaving group. Sometimes in E2 you get the Hoffman because of how the leaving group is oriented. Quiz on Monday when we